I'm Talia. I'm a high school senior who loves teaching others about chemistry and math. This YouTube channel is an extra resource for anyone who may be needing some help in their chemistry classes. This week, I'm going to be talking about dissociation, so if you would like to learn more about it, feel free to keep on watching. Without further ado, let's get started. Okay, so kind of as a background, before we get into dissociation, we are going to discuss water, because dissociation is when you put an ionic compound in water and it splits, the ionic compound splits into its respective ions. So water is a polar covalent molecule, which if you remember way back when we did bonding types and polarity, you calculate polarity with electronegativity values. And because it's polar covalent, there is a partial negative charge on the oxygen side and a partially positive charge on the hydrogen side. So when a compound is dissolved in water, the oxygen end of a water molecule, which is partially negative, attaches to the positive part of the ionic compound, and the hydrogen end attaches to the negative part of the ionic compound because, just like a magnet, for instance, opposite charges attract each other. So this then results in dissociation and hydration. So dissociation is when an ionic compound, like I mentioned, separates into ions, and hydration is when those ions are then surrounded by water molecules. So I have drawn a couple little diagrams here. So let's say we have potassium chloride and it dissociates. So we dissolve it in water. It will split into K plus and Cl minus, and the oxygen end of the water molecule will attach to the potassium plus ion, and the positive charge, or the hydrogen, of the water molecule will attach to the chlorine. And there's also a diagram of a water molecule. So the cation is surrounded by the negative end of the water molecule, and the anion is surrounded by the positive end of the water molecule. So how do we show dissociation? We don't draw a diagram every single time. We write a dissociation equation. So the ionic compound is a reactant, and the cation and anion are products. So just like with balancing regular equations, if an ionic compound has more than one of the ions, there will be a coefficient in front of that ion in the dissociation equation. Here's another example of the same dissociation. We have potassium chloride. This is the equation we would write, and here's a diagram. So in KCl, it's a 1-to-1 ratio, but if you had like MgCl2, you would just have 2 chlorine circles in your diagram, because MgCl2 would dissociate into Mg2 plus and 2Cl minus. So now we are going to practice with some dissociation equations. So we have CuSO4. So we want to separate it into the cation and the anion, and the cation is always written first. So we have Cu2 plus, and we know that SO4 has a 2 minus charge, so we have SO4 2 minus. And just like when we were naming multivalent ionic compounds, you know that this is copper. You know that this is copper 2 plus because SO4 has a 2 minus charge, and there's only one copper, which means copper needs to have a 2 plus charge to balance it out. Okay, so next we have KiO3. So potassium has a +1 charge, and iodine has a -1 charge. So I'm going to write K plus IO3 minus. Then we have Li2O. So lithium has a +1 charge, but there are 2 lithiums for every 1 oxygen. So it is going to be written as 2 Li plus O 2 minus. Okay, so next we're going to talk about dissociation and ion concentration. So these dissociation equations do have a purpose. One, they show what actually happens when you dissociate an ionic compound in water, but they can also be used to calculate the concentration of ions in an ionic compound. And we do this by multiplying the concentration of the solution by the coefficient in the dissociation equation for each ion. So if we want to calculate the concentration of each ion in a 2.0 molarity solution of sodium fluoride, there's 1 sodium ion and 1 fluorine ion in that solution. So we're going to write our dissociation equation. So it would be NaF yields Na plus F minus. So now the concentration of the solution is 2.0 molarity. The coefficient in front of sodium and fluorine is 1. We're just multiplying 2.0 molarity by 1. And that means that the concentration of sodium and fluorine will be 2.0 molarity. And it won't always work out so cleanly, because if you have a coefficient in front of an ion in your dissociation equation, then you will need to multiply the concentration of the solution by that coefficient in order to get the concentration of that ion. And this is how I would write my answer. And I use brackets, you use brackets to indicate concentration. So now let's do some practice. So we have 0.60 molarity K3PO4. So I'm going to first write out my dissociation equation, because I like writing it out and then putting the concentrations underneath. So if I have K3PO4, we have a 3 in front of the potassium. So that is going to be 3K plus PO4 3 minus, because phosphate has a 3 minus charge. So our solution, our concentration of the solution is 0.60 molarity. And then that means we are going to multiply 0.60 by 3 in order to get the concentration of potassium, which is going to be 1.8 molarity. And then for phosphate, there is just pretty much just a 1 as a coefficient. So the concentration of phosphate will also be 0.60 molarity. So I'm just going to officially write my answer. And when you write the concentration of the ion, you do not need to write the coefficient in there. Now let's try 0.30 molarity Al2SO4 So there are now going to be coefficients in front of both of the ions, because both aluminum and sulfate have subscripts. So I'm going to write out my dissociation equation again. So Al2SO4 is going to yield 2Al3 plus 3SO4 2 minus. I'm going to write my concentration of the solution, which is 0.30 molarity. And then because there's a 2 in front of aluminum, that is going to be a concentration of 0.60 molarity. And then because there is a 3 in front of SO4 2 minus, that is going to be a concentration of 0.90 molarity. I'm going to write that out. So now we are going to move on to dissociation and mixing. So when two solutions are mixed, you have solution dilution, because the volume increases and that decreases the concentration of each ion. So in solution dilution, you have C1V1 and C2V2. So to calculate C1, you use the dissociation equation, and to calculate C2, you use the solution dilution equation, with the final volume as the combined volume of the two solutions. So we are now going to practice an example. I have written out an example, and then you're going to do an individual practice. Also, just before we begin, if you have an ion that's present in both of the solutions, the final concentration is equal to both of the initial concentrations added together. So here's our example problem. Calculate the concentration of each ion resulting from mixing 70 milliliters of 0.15 potassium iodide with 80 milliliters of 0.20 molarity magnesium chloride, given that no reaction occurs. So you're just mixing them, they're not reacting. So I first wrote out the formula for both of those: potassium iodide Ki, magnesium chloride MgCl2. So then I wanted to calculate my initial concentration for potassium iodide and magnesium chloride. So I dissociated potassium iodide into K plus and I minus. And because the coefficient in front of both of those ions is just a 1, you do not need to multiply 0.15 by anything. The concentration initially of both of those ions is 0.15 molarity. Now let's go to MgCl2. That dissociates into Mg2 plus 2Cl minus. And there is a 2 in front of the chlorine ion. So you are going to need to multiply the concentration of the solution, which is 0.20 molarity, by 2 to get a concentration initially of 0.40 molarity for chlorine. Now I am going to just on the side convert my volumes into liters, because in the solution dilution equation, you need liters. And then those are both initial volumes. So I added them together to get my final volume. And then I just wrote the solution dilution equation down here, and I solved it for C2. Okay, so now if we go back and we want to calculate the concentration finally, like the final concentration of potassium, we can do C1 times V1 divided by V2. So we get 0.070 molarity, and because the initial concentration of iodine is the same, we can just write that the concentration of iodine is 0.070 molarity. You don't have to do the calculation again, unless your teacher requires it. Then we have magnesium chloride. So the final concentration of Mg2 plus is going to be 0.20 molarity, because that's C1 times the V1 divided by the V2, which is going to get 0.10 molarity. And then for chlorine, remember, we have a different initial concentration, so we have to do a different calculation to calculate final concentration. So I have 0.40 molarity, which is the initial concentration of the chlorine ion, times the initial volume, 0.080 liters, divided by the final volume, 0.150 liters, to get a final concentration of 0.21 molarity. I now have all of my concentrations, which I write using the brackets at the top of the problem. So we are now going to do an individual practice problem, where I'm going to give you guys a second to do the problem on your own, and then I will go over the answer. So in 40 milliliters of an 0.50 molarity solution of calcium bromide, you're going to write a dissociation equation, calculate the concentration of each ion in the solution, and calculate the resulting concentration of each ion in both solutions if the solution, so this solution, is mixed with 25 milliliters of 0.60 molarity potassium chloride. So give that problem a try on your own, and then I will go over the answer. Okay. So let's go over the answer. For the first part, we are going to write a dissociation equation. So I just balanced out the charges to come up with the initial compound, which for calcium bromide would be CaBr2. So CaBr2 is going to dissociate into Ca2 plus 2Br minus, and I just wrote over here, you write the coefficient in front of bromine, because you want to balance the charges in the compound. So now we're going to calculate the concentration of each ion in the solution, and I'm just using the same dissociation equation, but for bromine, the bromine ion, I'm going to multiply 0.50 by 2 to get a concentration of 1.0 molarity. For calcium, it just stays the same as for calcium bromide, because the coefficient in front of calcium is 1. So you would technically just be multiplying 0.50 by 1. And over here, if you wanted to, you could write the concentration of Ca2 plus equals 0.50 molarity, and the concentration of Br minus equals 1.0. Finally, we want to calculate the resulting concentration of each ion if the solution is mixed with 25 milliliters of 0.60 molarity potassium chloride. So I first wrote my dissociation equations for both compounds, potassium chloride. Both potassium and chlorine have a coefficient of 1, so the concentration of both of them is just 0.60 molarity initially. I rewrote my dissociation equation for calcium bromide. I do not know why I kept writing calcium chloride. There's calcium bromide. And then, so the initial concentration we already calculated in part B. Then I wrote out my volumes. So way up at the top of the problem, we have the 40 milliliters. So I converted that to liters, and then I converted 25 milliliters, which is the volume of the potassium chloride solution, also into liters. And then I added them together to get V2. Okay, so now to calculate final concentration, we're going to start with potassium chloride. So I have the initial concentration times the initial volume divided by final volume, and I get 0.023 molarity. I can also use that concentration for the chlorine ion, the chloride ion, because the coefficients in front of both of those ions are the same. For calcium bromide, I have my initial concentration for the calcium ion, 0.50, the initial volume, which is again in part 1 of the problem, divided by the final volume, and I get 0.31 molarity. For bromide, I have 1.00 molarity, that's the initial concentration, times the initial volume over the final volume, and I get 0.62 molarity. So I just wrote out all my concentrations in brackets, and these are our final answers for this problem. And that concludes this week's video. That was this week's video on dissociation. Next week, I'm going to be talking about solubility. So if you would like some help with that topic, feel free to join me back next week. As always, if you have any questions or comments, feel free to leave them in the comment section below, and I will do my best to answer them. Again, I hope you enjoyed this video, and good luck with learning the rest of your chemistry.